So hello and welcome to this Bioprocess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for Bioprocess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, John Bonham-Carter from Repligen.
Thank you, Leah, and welcome everyone, whether it's good morning or good afternoon to you. I'm looking forward to giving you a little bit of an update on Repligen's progress in clarification and harvest of cell culture bioreactors. I'm going to start by you've seen the agenda in front of you, but I'm going to jump over that in the interest of time and just jump to Repligen. Repligen is it's kind of an exciting company to work for. It's one of the 100 fastest growing companies in America right now. And I've been with them for about 4 years now, and it's been quite a journey. Started off Repligen with just protein A manufacture many, many years ago, and has transformed itself into a bioprocess tools company. And you can see that chromatography and filtration now are really pretty important in the portfolio of the company. And I'm involved in the filtration area. For the last 15 to 20 years, I've been involved with the XL ATF. Principally, this product is known for perfusion, and it's really done exceptionally well there. It's now the industry standard. And we're going to look at how this product can be used in a modified way in clarification to gain some of the things that you've been talking about in that poll to start with: simplicity of operation, hopefully increased yield, ease of use, and scalability. And those are all things I will talk to later on in this presentation. So when we look at fed batch intensification options rather than perfusion, which that product has been used for a long time, and in particular people who say, well, I've got a facility, I don't want to completely convert that to continuous, but how can I intensify my fed batch process with what I've got, with the minimum risk and the ease of implementation? So a very common way to do that today is with N-1 perfusion. There's lots of papers on this, and we'll happily supply those afterwards if you'd like. But the concept that this little graphic shows is the idea of putting a high-density seed into the bioreactor, let's say at about 10 million cells, and growing up to a higher peak cell density, and then finishing the process a little earlier, maybe as much as half the time it would take, instead of a low seed and continuing. And the goal here is to say in your final bioreactor, have the same yield or approximately the same yield, but finish earlier. But it's a single QC point, and you have the same downstream activities you would have anyway. So you're trying to do more in the same bioreactor and get a higher throughput of your facility. What I'm going to talk about today, though, is the high productivity harvest. So the goal here is to eliminate centrifugation, eliminate depth filtration, try and boost your productivity, and at the same time have fewer impurities, and we're going to be using a sterile enclosed system to achieve that. So you can see here the little graphic, what we're talking about. Instead of letting the cells die, we're going to start a continuous harvest, remove the product, and try and maintain the health of the cells to avoid the need for that depth filtration step. So when we look at the clarification unit operations, we've got a nice graphic supplied here. To be honest, I've yet to meet someone who loves a centrifuge in this particular process. And depending on your scale, you may or may not use that centrifuge, of course. But you'll have a depth filtration and sterile filtration prior to going on to the Crohn steps. But it's difficult. The depth filtration problems, I hear people oversizing it by as much as, say, 50% to account for the variation of the cell culture performance, depending on the number of cells, the viability of those cells, many other issues that people are dealing with, and a complex amount of preparation, the buffer prep, it may not be open. So I think while depth filtration works, and it works nicely, it's not people's preferred and ideal way of clarifying cell culture. So the question is, what can we do better? And we want to say, can we eliminate all of that, and can we make it a more robust and easier process? So we said, let's change the process a little bit. Let's start with that same fed batch process. So here we're starting from, say, day 0 to day 10, having a completely normal fed batch process. But on day 10, we connect the XL ATF device, and we start a continuous harvest of it. Could be as low as 0.1 VVD. So if you're in a 2,000-liter bioreactor, we're talking about, say, 200 liters in that diafiltration, gently removing the material that's there. But you could do it faster if you wanted. Up to 1 VVD would be our recommended maximum. And then you run that for 4 days in this scenario. And then at the beginning of day 14, let's say this is really the end of, let's say, Thursday night, you would then stop the media in, stop that diafiltration, and start a drawdown. So you're going to speed up the harvest pump to 1 to 2 VVD, vessel volumes per day, meaning you're going to empty this volume in the next 12 to 24 hours. And for those of you that like an LMH figure, 20 LMH is approximately where we'd be operating at. And so you'd run this for 12 to 24 hours, and at the end, you're going to finish your fed batch in the same time scale as you would have otherwise. But now you've emptied this vessel, you've harvested everything through into your harvest bank, and you're ready to go. So what does that actually mean? If you're a clarification team, what is the actual work? Typically, you might have got up on a Friday morning and been a bit worried about what that team upstream of you has produced this week, and you're going to be rushing to get that through the depth filters onto your purification team and handling whatever variation is put your way. Well, what would you now do? Well, on Thursday night, you'd be stopping this pump, and on Friday, well, I guess you could almost take the day off because you've harvested everything, right? There is no more steps, right? And that is very nice indeed. So you have eliminated these clarification steps here, replaced it with a single-use, aseptically connected device that goes straight onto the bioreactor. What's nice, of course, is these ATF systems. There's thousands of systems in the field. We've got 12, 14 commercial molecules manufactured with this. There's a huge amount of knowledge over this product and how it works. And it's very simple to scale down to a couple of liters to prove this process at small scale before scaling up. So we solved quite a few problems on that point. But what about the results? So when we look here and we say our red line here is our fed batch. This is Repligen data, internal Repligen data. Our red is the typical fed batch would have in Repligen on a CHO cell line. And then we've got 3 other processes here in green, orange, and blue, the 0.25 VVD line, a 0.5, and a 1 VVD. So you can see at this day 10, which is slightly arbitrary. You could do it before, you could do it after, according to what your facility can handle. You see here cell growth, of course, occurring as you remove waste metabolites and feed new nutrients. Of course, the cells will respond. And you see that in viability up here. So there is a still dip, particularly on the 0.25, but it recovers. So immediately you can see you're not producing many of those impurities you would otherwise as that viability drops. What does it mean in terms of cumulative product produced? So on this day 10 is when we've connected the XL ATF device, and you can see the different production profiles here. So in red is the fed batch, right? This, of course, is unclarified. This is a sample from the bioreactor. We haven't put it through a depth filter yet here. But all the others, 20% increase, 40% increase, even 100% increase, twice the amount. That is clarified, ready to go onto a column. So when people I've talked to say, oh, well, we got excellent results, 95%, on these data, there's very few people who've got more than 100% yield. And that's kind of a nice, fun fact to take back into your group to say, I can get more than 100% yield in this step today. But that's only one way of looking at it. You could say, yes, I want, particularly if I'm in R&D or phase 1, early stage, I love the idea of, in the same period of time, getting more product. That might be my prime goal. So I don't have to run so many batches per year. That might be my bottleneck. But that may be inappropriate for a later stage clinical or even commercial to say, how do I replace what I've already got? I've got depth filters, they work, but how might I do this? So you might say, okay, let's try and keep the same titer, but just harvest earlier. So in this scenario here, we started that harvest on 1 day. You've actually put through 1 vessel volume at this point, and you can now bring down the reactor if you so chose at day 11, and you've harvested the same amount as you would have done on day 14. So you might say that's more appropriate for my facility to put through. And of course, each of these profiles has a different amount of media views, so there's an economic cost you have to balance here. But the simplicity of this operation, the hands-free operation essentially, is a real benefit to everyone. And when we look at those volumes and you think, okay, well, what's happening to that final drawdown? Am I really capturing everything? This shows you the yield compared to the fed batch control. So in red, this is what you've harvested out of the bioreactor at the end of that process. And the difference between the red and the blue here is the amount remaining in the bioreactor before the drawdown. So clearly when you've got a higher harvest rate, a higher dye filtration rate, most of the product has already been removed. But when you've got a lower drawdown rate, and you might even be at, say, 0.1 or 0.2 VVD, you're definitely going to want to draw down that bioreactor. But remember, at the end of that bioreactor, when you say down to 20% of that volume, the vast majority of that is cells. So you really have removed virtually everything on that dye filtration step. When we look at some of the metabolite profiles here, you can see glucose matching each other quite a lot. On lactate, you see the cell growth, of course, happening on the larger flows that we've had. But at the 0.25 VVD, it's pretty much matching that lactate. And you see on ammonia also, the ammonia going up with fed batch, not such a great thing, but you have to handle it. But on both of the high flows and on the 0.25 VVD, the lower flow, ammonia being better. So these are going to be beneficial results to pass on to the purification team. And when we look at that purification, in our particular molecule, we see no difference in glycosylation and aggregation or anything like that. So there's no point showing that. But on the HCP levels, you see here on the fed batch, instead of being quite high, 150-ish here, because we're not allowing the cells to die, because we're not producing host cell proteins and DNA, actually our results show a dramatic reduction here. So this red, this is pre-depth filtration. So obviously before it gets the column, that would be reduced. But on our process, we're just not producing it. So therefore, you should end up with a higher quality of product or a higher quality environment for your product to be produced. And when we look at scaling, this is a key aspect. This data I've shown you today, we look and say, this could scale to 5,000 liters, of course, using 2 devices. We're a little conservative on these numbers. But we have people running this at 2,000 liters today in a GMP facility, working exceptionally well. So the scalability of this right from the small scale up to the large scale, the ability to match that and easily know what's happening so you can really make this a reliable process is a major gain. And I think many of you at the beginning on that poll identified that as a key deliverable for you. And so with that, the summary here to say, what is this high productivity harvest process doing? It's eliminating your centrifuge if you use one. It's eliminating the depth filtration. You can either use it to increase protein production without additional time. You could harvest earlier, or you could play around that and optimize it for your exact facility that you need. You're going to end up with a healthier culture with lower impurities. You've simplified that process. You've got a 0.2 micron filtered stream ready for clarification. And hopefully this is something that clarification team on Friday afternoon can therefore have a little bit of an easier job. With that, I'd like to take some questions.
Okay, great, John. Thanks. So the first question is, can you explain why the harvest does not need further conditioning before moving to a column?
Yeah, so people often think that when you come through the device, you're thinking that you're going to need to remove impurities or cell debris and so on. Because the filter used in the ATF device is a 0.2 micron hollow fiber, and that ATF action keeps that filter clean, what comes through is cell-free, debris-free, and is not requiring to remove that DNA or host cell protein or any other impurities that are created. Hopefully with that optimization, of course, they're not there, so you've got a drastically reduced burden onto your column. So it's perfectly ready for going onto a column.
Okay. And depth filtration can remove HCP DNA. If we use ATF, will those impurities be reduced? Do you have any data?
So that's a great question. No, if whatever is produced in that cell culture reactor, that will come through the ATF. But the goal of this particular process is to not create that in the first place. So it can't be completely eliminated, but just like depth filtration, it doesn't eliminate every aspect of impurities. But here we're saying, let's not create them, so therefore you don't need a depth filter to remove them.
Can you comment on the product quality, glycosylation, charge variant, sialation between the product harvested on day 10 and day 14?
Yeah, that's a great question too, actually. It's important to note you are changing the culture conditions here, of course, right? So typically in fed batch you're running for 14 days. Every day is different, and particularly in those last 2-3 days, the culture is dying, the viability is dropping, and releasing all sorts of those impurities into the system. And you're running at 37. So in this modified process, you're removing your product, putting it down to room temperature, or you could put it in a cold room if you wanted. So it's immediately in a better environment. The cells are staying alive, so all the impurities they create are not being done. So you could expect a higher quality of product. That doesn't mean it would be better if you're a biosimilar and you want to match a certain profile. You're going to have to tweak this to match that profile. But essentially, those glycosylation patterns and anything which interferes with that should be reduced. But that's something obviously needs to be looked at in R&D and looked on for your particular process.
Has this been applied to viral vector production?
So that's also a great question. We have people in viral vectors, gene therapy, vaccines. They use our device for media exchange, which is, of course, very similar to essentially a Dow filtration, prior to infection or transfection. In terms of using it for clarification, it depends upon the size of your product. So if your product is small enough to go through a 0.2 or a 0.5 micron, that would work. But if you've got lentivirus or something big, then that's not probably going to come through.
So where do the non-viable cells go?
So the non-viable cells, so those, that's the cell debris, basically. That is all being retained in the bioreactor. So a weakness of any filter, of course, is that it could block. So if you operate the ATF incorrectly or you don't follow our instructions, there's always a chance of this filter blocking. It's unlikely. ATF systems have been used at up to 300 million cells per milliliter for weeks at a time. So it's a very robust system. But it does mean all of those cells are retained. There is no complicated bleed or another control aspect that's required on this. So it's all staying in the bioreactor.
And how about the stability of filtration?
Sorry to finish. I was going to say at the end, of course, what's in that bioreactor in the ATF, that is discarded, right? So you've got a cell mass, a concentrated cell mass that's going to be discarded with a single-use system.
Okay. And how about the stability of filtrates stored for a long time at 20 LMH?
So that's a good question. You're removing the media into the harvest bag. Of course, in fed batch, you would typically have that in the bioreactor at 37 degrees C. Right now, you're removing it away from the cells. You're putting it at 25 or 20 degrees C. So it actually should be a better environment for that product. If you did think that there was a potential stability problem for your product, you could move into a cold room at 4 degrees. But in theory, this is a better environment than the typical fed batch process.
Okay. So there's a lot of great questions. We're not going to get to them all. I am just selecting the final question for John. And if we didn't get to them in this webcast, he will be able to follow up with you directly. So during drawdown, your culture volume would move past the lower impeller and would be unmixed for several hours. How do you get around this problem? Do you turn off controls halfway through drawdown?
That's a nice question, actually. So when you draw down, that's right, your impeller, depending on where that height is, it will be at the lower point. But in fact, the ATF system is exchanging quite an amount of liquid backwards and forwards. So that is creating some mixing. But naturally, as it gets down to that minimum volume and you're concentrating, let's say you've got 30 million cells per mil, you draw it down 5, 6 times, you might be at 100, 120 million cells per mil effective concentration, plus that cell debris. The ATF is working significantly harder, but it is mixing that remaining culture in there. And if you had a particularly valuable product or a particularly you had a particular need to get all of the product out, you could do a little diafiltration at that point. I wouldn't say so. But in all the experiments we've done at 2 liters and the people who've scaled up, our customers who've done it up to 2,000 liters, that amount of material is tiny as a percentage of the amount harvested. So while it might seem that you've got an unmixed amount and maybe the cells are dying, that's not actually the case. And at 20% or 15% of the culture volume, you probably can still agitate. You've probably still got a bit of air going through, and really you're in your last hour or 2 of the harvesting. And of course, your cell density was a more viable cell culture to start with. And I think it's worth stating that the cell culture media that you're using, right, this is just basal media, right, and potentially at that last little bit, you could just use PBS too. So you don't have to have a concentrated feed here compared to fed batch. You don't have to be using expensive media for that process.
Okay. So thank you, John, and thanks to our audience for joining us.
Thank you.
The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future Ask the Expert webcasts. Look for those announcements in your inbox. Have a good day. Goodbye.